What's up, everyone? Welcome to Simulation. We are with Dr. Stephen Kane right now. Thank you for joining us.
You're welcome.
We are going to be talking about planetary habitability, which is very exciting. And there's a lot to unpack around this topic. We are still at IPAC at NASA right now, and during the ExoCal week, this ExoCal conference that's going on, that's really important. And there's so much to talk about regarding astrobiology and how life has evolved on other planets and how we're finding that out. So we'll dig into that in this conversation. Stephen has a PhD in astrophysics from the University of Tasmania in Australia, and then he is now with the Astrobiology Initiative within NASA's Astrobiology Institute, and that is, you got about a team of 10 people that are working on planetary habitability, imaging missions, and your background's great. Let's run through this. So, this is exciting stuff. So we initially, when I was looking over what you were working on, I saw gravitational microlensing, and then you taught me about how, like, imagine back in 1995 when we were like, this is what we're going to be using to study it, and then like 10 years later we figured out that like transit photometry was like, wow, is significantly more advanced in finding habitability. So even just that realization for me was just so profound. But, you know, now having spent a couple decades in this industry, like, tell us about, I guess, that process and about, like, you know, how you feel about that and like where you're at now. Tell us about that.
Well, it was an exciting time when I joined this whole process back in 1995, because the field was really exploding at that time. 95 was when there was the announcement of a planet around 51 Pegasi. And it was a fascinating discovery because it was a giant planet in a 4-day orbit, and none of us really understood it. But it also caused people to project forward about, well, what can we do here? What's the path forward? And NASA had many roadmaps that they planned at the time. A large part of that was radial velocities, which was the method that was used to find 51 Peg, but also gravitational microlensing, which was seen as a way in which we could get to the really small planets. And so radial velocities, microlensing, those two in tandem were seen as two of the key parts going forward. And so I first got involved by studying gravitational microlensing as a graduate student.
And you were teaching me about this, and give us a bit on the radial velocity as well. But with gravitational microlensing, when you see this two stars that align with your path of sight, that you see some of that light from the back star get a little bit brighter, and then you can see if potentially there is a planet as well in between it, and then that light would slowly dip as it increases and then increase again, and you could
Right. Yeah, that's right. And gravitational microlensing was a theoretical proposal dating back to 1936, when Einstein had written a paper about this as a favor to a friend. Now, when I say as a favor to a friend, it's because Einstein didn't believe that this was an observable effect. He thought it would only ever remain theoretical. But it was based on his 1915 general relativity theories, because it involved the way in which mass affects light and space-time and things like that. As we entered into the 90s and the use of sensitive detectors on telescopes became more and more prominent, we realized that, wait a minute, I think we can do this, because the new detectors were allowing us to observe thousands of stars simultaneously. And by doing that, you're able to see these relatively low probability events, which Einstein had predicted. And the brightening of these stars caused by microlensing, because it's so sensitive to mass, it can in fact detect planet mass objects. And so in the mid-90s, the picture was that there was this realization that we could do this. It was still very much a theoretical study. It had been observed for some stars. There hadn't been any planets found, but this was one of the pathways forward as to actually discovering planets.
And that's like a big moment for civilization to be like, we figured out how to do this. And it's like a really hard way to do it. And then we figured out a much easier way to do it, which is still hard, but then we figured out the transit photometry. So yeah, I guess, how did that transition go for you?
Well, it was actually quite a natural transition into other methods because the gravitational microlensing method is very, very difficult. You only get one shot at this because these two stars lining up happens very rarely. So if you're able to scan a star for a planet, and you see something in the data, you can't go back to that star and verify it, or go to your colleagues and say, "Can you check this for me?" It's one shot, and so that makes it very, very hard.
In a million years.
Yeah, so the probability of those stars lining up again is about once every million years. So
versus every maybe dozen or hundreds of days with the transit photometry.
Right. Normally we want to go back and keep sampling a planet as it's orbiting the star, and we just couldn't do that with microlensing. But microlensing did start to discover planets, and at this point has found about 30 to 40 planets. But it's very much a statistical technique because we can't do the follow-up observations. But from there, I started to look into the transit method, which became popular around about 2000, because one of the known radial velocity planets, we observed it and saw that it transited its host star, and we realized, oh wait, we can do this. And we can set up cameras on the ground that monitor thousands of stars at a time and hopefully see something. And so I was building these instruments and developing ways in which to process the data, which were actually quite similar to the ways in which I processed the microlensing data, because both of them are looking at variations in brightness of many stars at once. So a similar technique that translated very well to transits.
Okay, so now that we've shifted to the transit photometry, your work then had been shifted in that direction. So you're continuing to make assisting with the Kepler telescope and that mission, and then TESS.
Yeah, so I was building ground-based facilities which were detecting planets. We're talking about 2003, 4, 5, and we started to find more and more planets using the transit method, and we realized this was a viable technique. And this was all leading up to 2009 when Kepler was going to be launched. And Kepler was essentially solving this issue of beating down the low probability of a particular planet transiting its star by just what I call the brute force approach. Let's just observe hundreds of thousands of stars at once, and we'll see something. And you can calculate what you would see because we can. There's a simple geometry that results in the probability that a planet will transit. And so Kepler was launched in 2009, wildly successful, but it was only observing at a particular patch of the sky. And also, Kepler was only ever intended to be a statistical mission. It was never intended really to be a mission in which we would follow up on a particular system, because we knew in advance that the stars were quite faint and that it would be difficult to follow up on them. So that's where TESS comes in, because TESS not only looks at most of the sky, but it's looking at very, very bright stars. And this gives us opportunity to do the kind of individual system follow-up that we couldn't do with Kepler for most of the time.
Yeah. And so that is very exciting. I think what is as exciting as, Kepler and TESS go up and do that is kind of like your behind-the-scenes analysis of what's going on with the catalog of all these exoplanet candidates, and especially the interest of the habitable zone planets. So let's start unpacking this.
Okay. Well, so the habitable zone is a difficult topic to talk about because it's a very misleading topic. And the habitable zone is somewhat of a misnomer because it implies the zone in which things are habitable. And because of that very obvious confusion of the term, which, by the way, doesn't just confuse the public, it confuses the majority of the scientific population. It's a real problem in the name. People have proposed changing the name. Nothing else has ever stuck. But the reason that we use it is because it's a phrase which was born many decades ago, back in the 1950s and 60s, where people started thinking about, well, where could we find liquid water? Where could water remain in liquid state around a star? And in the 1990s, people started to use computers to calculate climate models, which would quantify what this range was for the Earth. Yeah. And these were simple, what we call one-dimensional climate models. By one-dimensional, I mean they considered just simply a column of air from the ground up to space, and just look at the dynamics of that. But that was the first attempt at really trying to state, okay, this is what we can say about what the extent of the habitable zone is, which means how close to the sun would you need to move the Earth before it starts to evaporate its liquid water oceans? How far away would you need to move it before it freezes over? But the concept as a whole, because it's based on the Earth, is really meant to be a first guess. And that means that it's a concept which we primarily will be using in the years ahead for target selection. Which planets should we look at first? Because we'll have many, many more targets, particularly with the discoveries of TESS. Yeah. Then we will have follow-up resources to be able to look at. So we will need to make some very tough decisions. But for that reason, the criticism of well, the habitable zone doesn't tell you whether that planet is habitable, and that's absolutely true. But that's not what it's intended to do. It's intended to point us in the right direction, to hopefully lead us to what we know worked at least once, which is the Earth, of course, and then carry on from there.
So, okay, you're very... I like how you're so, realistic about things. I was telling you about this earlier, just that there's so much hype in so many of these industries. And so for someone to be like, yo, hey, let's slow down. Let's actually think about how we're thinking about things. And so in this case with the habitable zone, it's almost as though we've forgotten that life evolves potentially in even other places in our own solar system, in places that are not the habitable zone, like whatever's going on between Mars's crust and its core, and whatever's going on in Titan's oceans and in Enceladus and Europa, etc. And Venus, you actually specifically mentioned Venus a lot in what you work on, as well as what we were talking about, that if the sun gets brighter over time, that the Venus could have potentially been habitable and lost habitability. Keep unpacking this because it's so interesting.
Yeah, there's of course a lot of things that we don't know about habitability. We only have the single data point, which is the Earth, and there's a lot of objects within our own solar system that we know very little about. We don't know if there's life under the ice of Europa. Many suspect that there is, myself included, but we don't know. And the truth of the matter is that we're probably going to have to go there and drill through the ice and do some kind of sample return mission to answer that question. Now, if that's what we have to do in our own solar system, what hope do we have for a planet that's around another star? And
remote sensing is what
it's the thing to always remember about astronomy in general, of course, is a remote sensing science. Intrinsically so, we're extracting whatever information we can from what light we receive, and it's incredible what we can do, but we also have to understand the limitations of that. And so when it comes to planets around other stars, we'll never have in situ data for these planets. The only in situ data we will ever have is for the planets within our solar system. And so what we need to do, which is the common scientific approach, which is to gather what data you can and then create a model which you then apply to other systems based on the data you're able to extract for those. But the habitability within our own solar system is something that we still very much struggle to understand. Like you said, the sun has become brighter with time, which means that the radiation environment of the Earth is not the same as it was 1 billion years ago, 2 billion years ago, and the same is true for Mars and Venus. So there are ideas that Venus could have started with very similar conditions to the Earth. It could have had liquid water oceans. And as the sun became brighter, conditions changed on Venus. It lost its liquid water oceans. The water vapor moves to the atmosphere, and water vapor is a very efficient greenhouse gas. The surface warms up. On the Earth, the Earth has a place to store its carbon, which is the carbon silicate cycle, where the carbon is precipitated down onto the surface and moves into silicates in the rocks, which is subducted into the interior and then outgassed again. We call that the carbon cycle, or carbon silicate cycle. That's how the Earth is able to store its carbon. Venus, without liquid water oceans, had nowhere to store its carbon except the atmosphere. So that's where it all went. And so that's why we see the carbon dioxide dominated atmosphere on Venus now. But that was a process that took place. We don't fully understand how. And it's quite possible that many of the planets that we find within the so-called habitable zone of other stars are actually runaway greenhouses like Venus, that they could well be. But like I was saying, the habitable zone is not the zone in which things are habitable. At best, it could tell you that if there is water present, then it could be in a liquid state. That is the very best that it could tell you. It certainly doesn't tell you whether it's habitable. I've heard some people say that, well, water equals life because wherever we find water, we find life on the Earth. But the thing to remember about the Earth, of course, is that the Earth has been contaminated by life for 4 billion years. So at this stage, it's burrowed into the deep into the Earth's crust. Wherever we find anything on Earth, we find life, which is why after we spend so much time decontaminating rovers we send to Mars so that they don't carry anything with them. So water doesn't necessarily equal life. And so we have to be very careful about this term, the habitable zone, and understand that it is a very first guess in a science when we have to hold up our hands and say we are in our infancy. Yes. We do not understand this topic, but we are willing to explore and learn, and just take it from there.
Yeah, and I think we're going to end up potentially returning to this subject as we go throughout this conversation, because you were teaching me about this too. Is just this: there's not really a really strong conversation going on, a really strong relationship between planetary science here in our solar system and exoplanetary science. And you're explaining to this in the most relatable terms that this is all remote sensing. This is not sensing here. Sensing here is when you send to go drill into Europa. Otherwise, you're just taking light that's reflecting off the atmosphere or through the atmosphere or off of the planet from their host star, and that's traveling light years, and we're just getting the faintest of signals, and it's so much more, difficult.
Yeah. There is still a substantial distance that exists between exoplanetary science and planetary science, and one of the reasons that isn't obvious is because in your mind you can remove the exo from exoplanetary science and convince yourself that exoplanetary science is pretty similar to planetary science, but nothing could be further from the truth, because exoplanetary science, you have to understand that most of the methods that we use to find planets, particularly the terrestrial ones, and certainly this is true of Kepler and TESS, it's what we call indirect methods, which means we're not measuring the planet. We are measuring the star. We are measuring the effect the planet has on the star. And from there we are inferring the existence of the planet and the properties of it, but we are fundamentally measuring the star. And the history of this is such that the people who are in this field are stellar astronomers. They are people who understand stars very well, yes, and they're using the techniques that have been used to study stars for over a century. And these are just being brought to bear on this new regime where the object orbiting is comparatively small. And the problem there is that as we have become more and more sensitive to smaller objects, we've hit this regime, particularly once Kepler started producing data. We hit this regime where we were finding objects which were no longer giant planets like Jupiter. They're terrestrial objects. And we don't understand them. And the planetary science community looks in wonder at the science which is coming from exoplanetary science. But at the same time, they wring their hands at what they see us trying to do when it comes to, for example, understanding habitability. Because the planetary science community understands that for a lot of the things that we're trying to do with exoplanets, we can't even do for objects in our own solar system. So if I was to discover an object which was the mass of the Earth and the radius of the Earth, which is almost identical to Venus. Venus is 90% of the mass of the Earth and 95% of the radius. Within our uncertainties of our measurements, we couldn't tell the difference between Venus and Earth. And then what we try to do is model an atmosphere for it. Well, look at Venus. We understand very little. We've only sent a few landers back in the 60s and 70s. Those were the Russian Venera spacecraft, which only lasted an hour on the surface before they melted. And so we understand very little about the surface, the lower atmosphere of Venus. When we try to run climate models on Venus, they catastrophically fail most of the time. We have great difficulty in modeling the atmosphere of the planet that is the same size and mass as the Earth and right next door, and yet we try to do this for planets around other stars. This is the challenge, and it's going to require a deeper collaboration between the exoplanetary science community and the planetary science community, share that expertise, and hopefully find a path forward where we are able to construct this model that I mentioned, construct a model from in situ data that we can really effectively apply to planets around other stars. That's the real key forward to understanding habitability as a whole.
Yes. So we need to learn the kind of astrobiological models of our own solar system and how it has evolved across all these different planets to better understand or give us some sort of a better footprint as to when we have so much less data and so much more noise and so much less signal, how can we make sense of that with most efficacy?
Yes.
Yeah.
So another thing to remember about that is that if you're just looking at a planet, if you could imagine the state of our knowledge of objects within our solar system if we had never left the Earth. And by that, I don't mean manned missions. I mean if we had never sent probes to Jupiter or Saturn to the outer solar system, if we'd never sent landers to Mars or Venus or sent any spacecraft, and we were purely basing it on what we could see through the telescope, how limited our knowledge would be. The issue in exoplanetary science is that it's like that, except probably about a million times worse. Because at least we can resolve these objects. But it's important to remember that as a civilization, even as little as about 80 years ago, the people believed honestly that there was a civilization on Mars. It was just taken as fact. Yeah. And for Venus, particularly because we couldn't see below the cloud cover, there are movies from the 40s and 50s and so on that portray a civilization living on Venus. It really does require a great deal of actually going there and measuring to understand these objects. Otherwise, we could be greatly misleading ourselves with an incorrect model.
I really look forward to better imaging and understanding literally the planets next door, especially Venus. I'm happy that you've brought Venus into such perspective. So, okay, on your website, hzgallery.com, hcgallery.org, links in the bio, by the way, check it out, hcgallery.org. You can go and see a lot of all of the different habitable zone planets, and you have a counter on there. It's 125 or so. Yeah. Is that about what it is? Right. 125. So tell us about what you've seen in your categorization of the habitable zone discoveries we've had so far, as much signal as you can find from the data.
Yeah, so I calculate habitable zones, the extent of the habitable zone for all of the stars around which planets are detected, and then I create catalogs of these. I published a catalog of these for the Kepler mission a couple of years ago, but as you mentioned, I have this website which is meant to be all exhaustive for not just Kepler planets, but all kinds of planets which are in the Habitable Zone. And as I mentioned earlier, this is not intended to be a catalog of habitable planets, because we don't know. But it is intended to be a list that will provide guidance as to which of these would be most useful to do follow-up observations on first, if what we're interested in is finding the shortest path to potential biosignatures, evidence of biological activity on the surface that interacts with the atmosphere. And so it's difficult for using results from transit missions like Kepler and TESS in terms of filling out that space of finding planets in the habitable zone, because those methods are more sensitive to planets which are closer to their stars. And so what that means is that, and this brings Venus back into the spotlight again, which is that we are more likely discovering a whole range of Venus analogs first, and many of them. Which is exciting on its own if you're interested in Venus, but even if you're interested in habitability, sometimes people wonder, well, what relevance does Venus have to habitability? Because if you think of habitability as some scale where you have Earth at one end, then Venus would undoubtedly be at the other. But Venus could have been habitable at some point, and that's something which is actually taken into account in calculating the boundaries of the habitable zone. There's additional boundaries called the optimistic boundaries of the Hubble zone, which extend it slightly further under the assumption that Venus could have had liquid water on its surface up until some late stage in its history, as the sun got brighter. So we have limited numbers at the moment. Like you mentioned, there's about 120 or so planets in the catalogue which are known to be planets in the Hubble zone. But it's really
candidates for us to keep looking at.
Yes, and I should say, by the way, that the catalog does not discriminate on size of the planet. You can certainly you can categorize that within the catalog yourself if you're only interested in terrestrial planets. But it also shows you giant planets which are in the Hubble zone, because it's an interesting thought experiment to ask, well, what would the Galilean moon system be like if they were at Earth's orbit? And so giant planets and potentially habitable exomoons, that sort of thing, is also taken into account in that catalog.
Yeah, this reminds me a lot of our conversation that we were having earlier about crunching all of these variables, because what would it look like if we had like a 28 moon system or around Earth, or what it would look like if the star was a little bit dimmer or the star was a little bit brighter. All these different what if statements are basically what exists in other solar systems, and it's just up to us to go and discover it and find it, or run the simulations here and try and figure it out. But I really like that aspect of calculating variables and seeing how things evolve, and just having a better desire for our own understanding of astrobiology in our own solar system.
Yeah, it's true that there are many variables, and it's another thing that we need to be mindful of when we're considering the differences between what we learn about exoplanets, what we learn about the objects within our own solar system. The transit method tells us the size of a planet. That's our step one, if you like, when we're learning about the properties of a planet from something like test discoveries. Then we follow it up with a different method, typically the radial velocity method, and we measure the mass. What do we learn beyond that? Then it starts to become very, very difficult. Once the James Webb Space Telescope is launched, we will, of course, follow up the planets which are in the habitable zone and see if we can measure the atmosphere. But even then, there are many things that we haven't measured. We have not measured the rotation period of the planet. We haven't measured the obliquity, the tilt of the axis. Yes. Like for the Earth, it's 23.5 degrees, which gives us our seasons. We won't have measured that at the point when we get these atmospheric observations. And if it's tidally locked or not, that's something that we try to calculate from a theoretical point of view, but that is difficult because it depends on a lot of intrinsic properties of the planet as to how long it takes to become tidally locked. So there are a lot of properties of the planet which are still out of our reach, and the question is, those properties that we can't yet measure, things like the rotation period, do they have a strong effect on what the surface conditions might be like, which is what we ultimately care about? And the answer is yes, they have a huge effect.
That's that variable.
And so there's still a long ways to go. It won't be until we can directly image planets that we actually start to unlock all of the first order properties that really drive the climate. And so that's going to take a little while longer.
I love the idea of imaging our own solar system first, and at least simultaneously. We need more funding in all these projects in order to be able to do so simultaneously. Okay, so this has been a really thought-provoking conversation, a very realistically, grounded conversation about where our attention should be in a very realistic sense, in a calm sense, and not necessarily living in a super hyper excited sense. So I really appreciate that a lot. Okay, so how about we talk a bit about what's going on with the next generation of evolution on the planet regarding space. We're sending, TESS is up now, James Webb's coming up after that. The space economy is going on, some Japanese billionaires orbiting the moon next, and we have all these small sat companies. Where do you really think about the space economy in the future and what that means for us moving forward?
I think any interest in space is good. The issue when it becomes commercialized is that, well, we're not wanting to sound obvious, but it becomes commercialized. In other words, it becomes about what is the profit margin of this enterprise. I have spoken to many of my colleagues about why did you first become interested in astronomy? Why did you decide to pursue it as a professional career? And never once did any of them say, oh, because I hoped that a byproduct of my research would lead to the next generation of Velcro or something like that. Never once. It's always been because they have an intrinsic interest in the science, and we see that as something of value to society. I think it's imperative to society that we have this intrinsic interest in the universe that goes beyond commercial exploitation of that science, which is sometimes what is referred to as the spin-offs argument. Is if it wasn't for this space enterprise, then we wouldn't have this medical device or something like that. But that's not why anybody does it. And we should be real about that, and we should also be real about the fact that this is something which encapsulates the imagination of many young people to get interested in STEM, in various science projects, and pushes the boundaries of this forward. And removing that kind of enterprise is kind of similar to removing arts and music and things like that, the things that make us human. So so that's the downside of it, in the sense that I would like to see more interest in all avenues, but let us never lose sight of why we're doing this in the first place and why we're really interested in this.
Man, that's really important what you just said there. It's just who gets into astronomy because of the big bucks? People get into astronomy because they fall in love with it, and that they want to bring this to the world, and of its straight importance to inspiring us to understand our oneness and how we best progress moving forward sustainably. Okay, a couple of these last sort of questions as we come to an end. Do you think we are alone in the cosmos?
That's something I've thought about a lot, and about the Fermi Paradox and the explanations for it. And when you look at the history of life on Earth and how quickly life evolved, and the fact that life did seem to start pretty soon after the Hadean period when the Earth was cooling off, and you look at the frequency of terrestrial planets out there, You look at the history of evolution on the Earth. Sometimes we can tend to think of humanity as being some kind of apex of the pyramid of evolution, that it all leads to us. Evolution doesn't necessarily favor the ability to build a spaceship. It favors reproduction and adaptation to environment.
Dinosaurs would still be around if it wasn't for
we would all still be speaking dinosaurs if there was not the KT event at the end of the Mesozoic, for example. From this, and considering how long it took for a complex life to evolve on the Earth, my feeling is that organic, like basic kind of life, is actually pretty common. That basic life, single cell, that sort of thing, is a natural consequence of a planet having liquid water on the surface for long periods of time. That would allow it to have a stable climate. I think intelligent life is quite rare. My feeling is
lots of other things could evolve that are not potentially intelligent life.
And one of the issues in all of this is of course we can't help but be anthropic about it, and we bring that to the table whenever we think about, well, how would we recognize intelligent life? Some people say we don't know what we're looking for, but we'll know it when we see it. I'm a little more skeptical about even that. I feel like we won't know it when we see it, or maybe only 5% of the time. And because we make enormous assumptions about how they would communicate. The Sagan story about contact famously proposes that prime numbers may be some universal language, but who knows? That's not necessarily given at all. It's so difficult to separate ourselves from our worldview that I think it's almost impossible to predict how that communication would happen, and therefore if we would recognize it at all. So my prediction is that intelligent life is extremely rare, that the physics required to travel the large distances may unfortunately not exist, and that may be a huge stumbling block. There could be a number of reasons.
Yeah, you brought that up earlier too. I'm glad you said it again, that it just we just may explore our own solar system and then just enjoy our solar system, maybe try and get to Proxima Centauri, and because it'll still take us hopefully 20 years to travel 4 light years, or whatever. So this is tough stuff. The physics are not in our favor, and so maybe civilizations turn inward when they achieve this singularity. Maybe that's part of the equation. What do you think is, if we're in a simulation or not?
It's I've heard a lot of people give talks about this whole concept about whether we could be in a simulation, and I find them really interesting in a philosophical and intellectual sense. That it's kind of one of these cool Black Mirror-ish things to explore. If we never know the answer to that, it won't bother me at all, because if this is a simulation, it's an awesome one. I'm loving it. Good job to the creator, So I don't know if it's something that we'll ever be able to fully answer. And in fact, I'd be awfully disappointed if somebody created some philosophical argument that went through a bunch of logical steps and concluded that we are not, ergo, we are not in a simulation. That would be terribly disappointing, because even just having it out there as a tantalizing possibility, I find, as I said, philosophically, intellectually, it's kind of fun.
It's hella fun. And then we're moving towards indistinguishable virtual worlds that we get to design and go live in. And so you could already be living in one of those for 80 years right now. Right. Okay. Let's ask you, just 2 more questions. Second to last question is, how should we maximize human potential?
Wow, that's a tough one. The answer to this question, and this is related to something that we were also talking about earlier, it appears to be time dependent. Many people of our vintage and older have seen society changed significantly over the last couple of years with the internet and social media and the ways in which people are using their time, and it's something where, at the risk of sounding like somebody who's not nearly as old as this makes me sound, but related to attention span, the ability to focus on tasks. And the reason I say that is because that is, I think, a fundamental part of becoming absolutely drawn into and fascinated by a subject if your interest can only be held for a short period of time. And it's just extraordinary to me how hard it can sometimes be to get people interested about not just astronomy, but general life sciences, earth sciences, space sciences, as something that, wow, I can't believe that we're actually doing that as a civilization. That's incredible. And I want to learn more about that. Instead, you have to fight against, Pokemon Go and various things like that. But it's something which creates an extra challenge to science education. And I believe it's a solvable problem. There of course, I don't want to be too general in the way I'm talking about this, because there are still vast waves of people who are coming into science. We see this in exoplanetary science because it's growing so rapidly, and that couldn't happen without huge amounts of interest. So it's something that we just need to adapt to the way in which information is passed on and processed, and hopefully that will help increase our potential in answer to your question. But I do hope that as a civilization we continue to recognize our small place in this universe and respond proportionally to that realization in trying to understand it. That's the key.
Yeah. That last part is so good, and so is what you said earlier. It's a paradox. We are both nothing, a grain of sand, but we're also everything. We're divine, and it's beautiful. But also the notion of focus. Focus is so crucial with the birth of this last couple of generations, especially the one that I grew up in, the one that's growing up right now. The smartphone babies and stuff like that. This is going insane if we're not able to be very careful with manipulation, propaganda, deep fakes, psychometrics, all this type of stuff. We're gonna have generations of manipulated and that are just not focused on the important things that we need: education, prosperity, actualizing their own souls into the world, all this type of stuff. So I'm glad you brought that up as a huge pillar of it. Okay, Stephen, last question. What's the most beautiful thing in the world?
My answer to this is going to sound slightly cliched, but I will say that I think the most beautiful thing in the world is the universe. I fell in love with the universe when I was very young. I grew up in Outback Australia. And I had a trampoline in my backyard. When I was a kid, at night, I'd go and lie on that trampoline and just look at the stars. Yeah. Fell in love with it then. It's been my mistress ever since. Yeah. It's the gift that keeps on giving. Yeah, it is. And it's something that makes me unable to relate to folks who create conspiracy theories or, feel they have to add a layer onto reality, because if reality isn't enough for you, then you're not looking hard enough, in my opinion. I think that the universe is just this fascinating thing that we could spend eternity trying to understand and really, really enjoy it.
Yeah, I love that. Beautiful answer. And I hope we can give as many children as possible that sort of laying on the trampoline in the middle of the outback and looking up, because that definitely does a great deal of inspiration and ego dwarfing for adults. We get out there and get that ego dwarfed. What a pleasure this has been, talking about habitability, about exoplanets, about it's the actual science of local astrobiology within our solar system. This really difficult signal that we're getting from far away. This makes it very difficult, but it's very realistically grounding, and I really appreciate that a lot, Stephen. Thank you so much for joining us on the show and talking to us. Really appreciate it. Everyone, if you had a good time, definitely give us a comment below. Let us know your thoughts. We'd love for you to join the conversation. Also, don't just consume. Go and create. Go and make cool things with this. Go and make art, make music, make shows, make books, make businesses. Go and create with this content. Also, check out hzgallery.org. The link's in the bio. Definitely go check out the Habitable Zone Gallery that Stephen put together. And thanks, everyone, for tuning in. We greatly appreciate it. Much love.